Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number, I think we skipped one in the middle of the week with the hurricane and me being out of town. So let's call it number 2, okay? And we're going to be talking about something called storm relative wind or storm relative velocity. And this really came into play the other day in Florida when Hurricane Milton was generating all of these tornadoes. And we're going to focus on one particular cell that the National Weather Service office in Melbourne, Florida picked up on and used this technique to detect an area of rotation and to issue a tornado warning as a result. And I think they actually issued something like 60 tornado warnings the other day, just that one office. And then of course there were other offices in Florida that were issuing tornado warnings as well. And I'm sure you know by now that several of those tornadoes actually generated some pretty significant damage. So, and that was independent of the damage that was caused by the hurricane itself with its winds, okay, on a much larger scale. So let's go on ahead and put myself down here in the corner. We'll just review a couple of concepts here first. And the first one is that whatever weather system you're talking about, a severe thunderstorm, a tornado, a winter storm, a hurricane, there's winds that they're generating on their own, okay? So all of these systems in the northern hemisphere are going to generate a counterclockwise flow. And you know what I realize is when it's counterclockwise for me, but it's clockwise for you. So if I want to make it counterclockwise for you, I need to, I guess, go like that, right? Okay, whatever. Everything's reversed. But anyway, all these systems generate this counterclockwise wind flow. But they are also embedded in a larger scale flow, okay? A steering current, if you will. So you know how we talk about the jet stream winds and the upper level steering currents? Well, that's operating on a much, much bigger scale than the system itself. And so it is being carried along in that flow. And of course, we use that information to predict where systems are going to go. So in order to see how much wind the system itself is generating, we have to subtract out that large scale flow and then see what we have left, okay? And so this is very, very useful when it comes to severe thunderstorms and especially tornadoes. And so I'm going to show you one example of how this came into play the other day on Wednesday. So here you're looking at a product called base velocity, okay? And maybe an even better term for it would be raw velocity, okay? The Doppler radar is up here, in this case, in Melbourne, Florida, where that little open black circle is. And the cell we're going to be looking at is down in here. So the way Doppler radar works is it detects winds that are either coming toward it or away from it. And the accepted color code for that is that greens are going in toward the radar, and they're designated as a minus sign, okay? And then the reds are outgoing velocities, and they're denoted with a plus sign. Now, here's an interesting thing about Doppler radar. It can only detect winds that are coming in directly toward the radar. We actually call it radial velocity. So, in other words, if a wind is blowing from the south, okay, and it's blowing right along that radar beam, then it will detect the full value of that wind. But what happens if the wind is actually blowing across the radar beam, okay, at an angle? It can only pick up the component of that wind that is blowing directly in toward the radar, okay? So if you had a 100-mile-an-hour wind that was blowing perpendicular to the radar beam, it would show up as 0 because there would be no radial component coming in along that radar beam. And so this is why you have to be really, really careful and take a look at what direction that wind is coming from and what direction the radar is pointing at any one given moment in time to make sure that you're not missing something here, okay? So if a wind is coming in from the southeast, in order to get the full value of that wind, you would want the radar beam pointing southeast, and so that way you would see the entire velocity blowing toward the radar. But if the radar beam is pointing toward the southwest and the wind is coming in from the southeast, it ain't going to see nothing, all right? And so again, that's something you need to account for. So the greens are coming toward the radar, the reds are going away from the radar, and so think about being at Disney World and your kids are on a merry-go-round. Well, at any one moment, those kids are going away from you, but a few seconds later, they're on the other side coming toward you. So if you're looking at a tornado and half the raindrops are going away from you and half are coming toward you and they're right next to each other, that tells you those raindrops are spinning, okay? So you want an inbound right next to an outbound, showing you that that rotation is there. Well, do we have that here? Well, we've got a lighter shade of green here, a darker shade of green here, but they're all coming toward the radar. So we don't have any spin, do we? Okay, now if you want to get into shear arguments and all of that, yeah, you can do that. But just from a color perspective, everything's coming in, so there's no spin, right? Okay, and what are those actual values? Well, in this particular case, on the one side, the winds were coming in, that's what the minus sign means, in toward the radar at 107.4 miles per hour. On the other side of the cell, they were much lighter, but they were still coming toward the radar at 20.1 miles per hour, okay? So it's all greens. There's no green and red next to each other, so nothing to worry about, right? Wrong. Okay, let's go to this next product here, which is called storm relative velocity, where the movement of the storm is subtracted out from the winds that the radar is actually detecting. So we had a minus 107 and a minus 20, right? Well, now that minus 107 became a minus 60, and the minus 20 became a plus 25.7. And now we've got greens next to red showing rotation. How did that happen? Well, the storm movement in this particular cell is from 186 degrees at 47 miles per hour. So 47 miles per hour of that minus 107 was being generated by the large-scale flow. So if you take 107 and decrease it, okay, by 47, then you get about an inbound wind of minus 60, okay? On the other side, that minus 20 that was coming toward the radar, well, if the movement of the system is 47, then that means the storm is not generating any inbound wind at all. It's actually generating an outbound wind, okay? And if you do the 47 exactly, you should get plus 27, and we get plus 25.7. So there's probably a little bit of an angle coming in there that's making those numbers not exact, but it's awfully close. So by subtracting out the motion of the storm, okay, then you see what the system itself is generating, and it makes it much, much easier for any radar operator to see those areas of rotation, because now you have the greens and the reds adjacent to each other, and the higher those values and the bigger the difference, then the more rotation you have. Like in this case, you have a minus 60 and a plus 26, if you will, if you're rounding up. So that's 80, let's see, about 85, 86 miles per hour of rotation, okay, which is pretty significant. So this is a tool, and of course, again, the National Weather Service radar can only detect winds that are coming in along the radial, whatever direction that the radar is pointing. And so, again, that's something you have to be careful with to make sure that you're detecting the full value of the wind. So you want the radar beam going out in the direction the wind is coming from or blowing toward, and then you will get that full value. Otherwise, it's going to be reduced, and if you're looking at it at a 90-degree angle, it's going to go away, which is not what you want in this type of situation. So I hope that makes sense, and this applies to not just tornadoes, but also hurricanes and winter storms. It's just that usually we're more interested in this on a small scale where you have severe weather, tornadoes that are operating in a very small area, as opposed to a storm that is affecting multiple states, okay? This technique really comes in handy when it comes to small-scale systems like tornadoes. All right, folks, I hope you found that interesting. That is bonus weather video number something for this week. I hope you enjoy what little bit is left of your Friday evening and you have an even better weekend. And we'll talk to you again on Monday. So you all take care, folks. We'll talk to you soon. See you later.